Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and I'm glad you have taken the time to join us today as we look at our topic of how to collect and analyze torque measurement data. Now, there are a number of values to measuring torque data. And obviously, when you look at something that you want to try to improve, you need to be able to measure what's happening with that situation. And so as we look at it through the lens of our applications and our processes, and as we focus on our tool measurement of our torque values, this gives us a real closer look at how a specific tool may be performing in a certain area. It also gives us the ability to check for root causes that we may see within a particular application that may be giving us some issue. And we can look to check to see if the tool is the problem there within that process. It also gives us the ability to document what is happening with a particular tool or a set of tools. And this can be really useful for any type of ISO 9001 type of audit where you're looking at whatever your process might be and steps that you're taking to make improvements with that. And then also gives us the ability to track how a tool may perform over time and how accurate that tool might be for that particular application. And so what are the different stages throughout the application process that we can use our torque analyzer to measure and gather torque data from? And there are three basic stages for that. First is going to be prior to the assembly, next during the assembly, and then you guessed it, after the assembly. And so prior to the assembly, we're looking at the way we set up a particular tool for an application. It can also be used for tool capability studies and R&D. And then during the assembly process, we're looking at the torque verification and torque validation process. And then after the assembly, we can do some torque auditing and then torque recalibration for a specific tool. And so in these areas, we'll go over a couple of different examples of each. And then that should give you a little better understanding of how you can look at your process and determine what might be the best route for gathering torque data. And so that's going to lead us to our poll question today. And so if we'll go ahead and launch that poll, it's going to be when do you collect your torque measurement data in your manufacturing process? Is it before the assembly, during, after, or during the annual calibration? So we'll go ahead and get that going, and then so when we get those results in, we'll go ahead and publish that. All right. Thanks very much for participating in the poll. The runaway winner there is going to be during the assembly process, followed by after the assembly process, and then once during the annual calibration, and then before the assembly, followed up the last answer there. So thanks very much for participating in the poll. So when we look at during the tool setup, what we are basically doing is if we were to remove one tool from a work area and we're going to be putting that into another cell or another application, we will need to go ahead and make adjustments to the torque value for that. And that could be done with a preset tool. We can also do setup on an adjustable hand tool. We want to make sure that we're consistent through the range of the tool. And this can also be during a power tool setting as well. Could be an air tool, could be an electric clutch torque screwdriver. And that would be when we would be using our torque analyzer at the tool setup portion of before the assembly process. And then that is typically done with an analyzer like this, where you have an internal sensor that you can use, or you could even use an analyzer like this that also has a torque sensor built into it, but it also has the ability to expand the range of the analyzer by giving it the ability to add additional sensors to that, expanding its range. So for example, if the internal range of the analyzer went from 5 to 50 inch-pounds, but we also then needed to get up to 250 inch-pounds, we could then add another sensor that would have a range of 25 to 50 inch-pound, or excuse me, 25 to 250 inch-pounds, giving us the ability to test outside of the range of the internal, but we're still utilizing that analyzer for that ability. And this can be used again to test a hand tool, either on the internal or the external sensor, and also then setting up an electric tool with the use of a rundown adapter or a joint simulator for that tool. Because when we're doing an electric tool, we want to make sure that the tool gets up to its RPM speed and then shuts off, because the inertia that happens when a tool shuts off is part of the torque delivery. And so we want to make sure that we're using a rundown adapter for an electric tool during that setup period. So next is going to be basically during the assembly process, and this can be used for the torque verification and torque validation process. And what this is very very important, because if you're sending your tools out on a annual basis or some type of predetermined time basis for your tools to be calibrated, if that tool comes back and the as found reading is outside of the tolerance, that can be a real issue, because you really have no idea at what point did that tool go out of calibration, what parts may have been used on that particular tool. Is it a critical type of application? Is this going to cause us to do any type of rework, or are we going to be needing to contact end users or subcontractors that we've had an issue with this tool? And so the torque verification and torque validation process allows us to be able to test a tool actually during the actual assembly process to validate and make sure that it is still within its torque specifications. And so that can be done with the use of an analyzer like this and a rotary type of sensor. This allows us to be able to put that sensor in between our tool and our part, and we can go ahead and use the tool on our part and still capture the readings that are going on for that. So we can verify that that tool is still within its specification. And so that range or frequency can be determined by how important that particular application may be. Is it something that you do once a month that you do the check, or is it once a week, or is it once a shift? It just depends on the criticalness of that particular joint. But the torque validation and verification process can be extremely helpful in identifying tools that may be drifting, that may be on their way out of calibration, and those tools can be then set aside for repair or service to make sure that they stay within their their range that's needed for that particular application. And then we also have customers that will not base their calibration of a particular tool based off of time. They base it off of how that tool performs in that particular application. And so they will do this validation check at a certain frequency. And as long as the tool is still within the operational limits, then they continue to leave that tool on the floor and keep using it until it shows signs that it may be getting close to needing some adjustment or recalibration as well. And so the torque verification process can help you to extend that, and you then are collecting all of the data that is being used for that particular tool on that particular application. So there's another way that we can do that, and that would be the use of a barcode scanner on a particular tool. So if you want to go out to the line with the unit for the built-in transducer, in this case we can use a barcode scanner in our tool test function. So we go ahead and enable the tool test function. That gives us the ability to scan the tool. It will automatically pull up the limits and the test criteria for that tool. It will take the particular readings or number of readings that we have set up for that tool. In this case, I think we have 5 set up for this test. And then after the 5th reading, the unit will go ahead and reset. And now all of those readings that the tool has been used or within that particular test are all time date stamped. And again, it gives us the ability to look at how the tool is performing during the validation or verification process. If you don't necessarily want to use a rotary type of sensor, you could still use the internal sensor on the torque analyzer to do that. And the tool test function is an easy way for you to grab that information, again, with the time, the date, and the data for that particular tool on that particular test. And so one thing that you may hear as it relates to testing and getting torque values is going to be static torque versus dynamic torque. And if we look at the definition of a dynamic torque, that's the measuring during the dynamic assembly process as the fastener turns as we're applying torque when it's achieved. And so that could be done, again, with a hand tool. It could be done with a power tool, but it's the use or the measurement of a particular fastener as it's being installed. And then if we look at the definition of static torque, this is where we're measuring a particular fastener that has been already assembled, and we're trying to get the torque value from that particular reading. And so that is the basic definition between the tool. You may also, this may be also used in how a sensor may be categorized. So we have a rotary sensor and our static sensor, which would be our BMX, which the drive in there does not move, it doesn't turn, but it is capturing the actual torsional forces that are happening with a particular tool. And then the rotary sensor or the dynamic torque sensor allows that to freely spin and get the torque information, allowing the tool to be used in line with our application. And so those are some things that you may see in regards to sensors. And then there's also sometimes tools may be referred to as a static tool or dynamic tool. A hand tool may be considered a static torque tool, and then a power tool would be dynamic. And so those are some of the things that you may hear about or terms that may be used in that way. And so when we're looking at torque auditing, it's very important that we understand that what we're looking at is the static torque testing of a fastener that has already been installed. And so there are a few different tests that you can use that will allow you to do that. The first is going to be the first movement test, and then next will be a loosen test, a marking test, and this all kind of falls under the umbrella of residual torque. Now, there technically is no residual torque once a tool has left the fastener, and the fastener is just there. There's no actual torque because torque is a measurement of movement, but nevertheless, that is a category that might be used to do that. And so we can use rotary torque sensors to be able to do these types of tests. And let's kind of go over what those tests look like. And so the first movement test is where we put or we actually turn the fastener a few degrees in the tightening direction, and we want to be able to capture what that value is during that movement. And so this can be a good test to be able to determine what the torque value may be on that fastener. But we typically want to measure what that value is at between 3 to 10 degrees of movement because there are some frictional forces that we need to overcome during that particular test. And so if we look at that on a graph, when we go ahead and we apply load to a fastener and we've reached the torque value, then we remove the tool. There is the amount of torque that was used to go ahead and fasten that bolt or screw. But there are some frictional forces that we need to overcome to be able to move it again to check it. And so this is kind of an example of just the coefficient of friction. If we have our block here, which we have our forces pushing down on it, which is gravity, and then as we try to move it in a tangential force, we have what would be our coefficient of friction as our block moves. However, there is a point where we need to be able to overcome the threshold of movement, and once we do that, then we can have our constant friction. And sometimes that threshold of motion is actually higher than our frictional forces. And so that's what we're looking at when we go ahead and we add additional torque to that fastener or additional movement. We may see a rise in the torque, then it dips back down, and then it would be keep going as we apply more angle to that fastener. So at about 3 to 5 to 10 degrees or so is typically where you can see what the value was when the tool was applied or when the torque was applied. Again, this is a test that can be done with the rotary sensor. There are some tools out there that will allow you to do this, some torque and angle wrenches that could do that as well. But it's important to be able to try to capture that reading at the point once we move past the frictional forces. The next test is going to be the breakaway test. And this is when we actually just turn the fastener in the loosening direction and see what that value is. Now, this is typically not very accurate because there are some torsional forces that are in the fastener itself. And once you start moving it, that can play a part in the value. And in some cases, you may see a lower torque than what was applied. And so this type of test is not great to be able to use as something that you might want to continuously do. But again, with the first movement test and with this test, and with what would be the next to it be our marketing test, it all gives us the ability to look at certain values based off of uncertainty and correlation to whatever value we receive when we do the test versus the value that we see when the original torque was applied. But the loosening test, again, is the least accurate of the auditing tests that you may see. Next is going to be the marking test. And so this is very simple. We simply mark the part and the fastener in a line. And then we go ahead and break the fastener away. And then we bring those two lines back together and we see what that value is. And again, this is going to be a little bit more accurate than some of the other two tests that we looked at. But again, it is going to be very application specific. It's going to be very material specific. Again, trying to replicate the actual frictional forces that are happening during the original assembly and with the test is going to, again, give you results that may not exactly match that we're going to be at the install. But again, if you can develop a correlation and a certain uncertainty about what those values mean, then you can go ahead and trust that when you get a certain value, when you do the marking test versus what the actual install value is, then you know that you're getting the correct value at the installation based off of your uncertainty that you may see there. And so this kind of all leads us into the ability for process control and tool capabilities. And doing those types of tests can really help with either if you're having issues with a particular assembly process or the overall assembly of a specific area. What you'll want to do then is you can do your CP and CPK testing. But the first place that you should start is going to be with the CM and CMK testing of the tool that you're using within that particular assembly. And so this difference is because we're not testing the actual process itself. We're just utilizing the tool to make sure that it's going to be within our limits. Because if the tool is out of the limit, it's not going to do anything. It's going to make the CP and CPK values fail. And so if we can isolate the tool at first, we can then do our testing for those CM values and CMK, which it's basically the same type of testing, but we're just doing it on the tool. Now the tool, we want to be able to use it continuously without basically stopping or within what would be considered the process. We want to make sure that there's nothing else that is going to be influencing the test, whether it's the operator or the time of day, the environment. We just want to test how the tool is functioning and get those abilities. Now, we have a video clip here of a test being performed a while back. And so we set the specification for the torque limit at 10.8 inch-pounds. And that's going to give us our target value at 10.8 on our Easy Torque 3 here. It also shows us what our minimum value is and our maximum value is. And we're measuring in the peak mode. We then can go into our advanced mode, and it's going to allow us to calculate the CM and the CMK as we do the test. And so you typically want to run at least 25 to 50 or so values to be able to get a good test on your tool. And in this case, we did the test to 40 cycles. So we can get a good representation of how this tool is performing. And then again, it gives us the ability to look at what our CM and CMK is for that. And so in this case, we did 40. Our CM, which is a great value at 2.75, and our CMK at 2.55. This shows us that in our process, our tool is performing well within the specification for that particular torque setting. And if we look at our standard distribution curve, we have our lower limit and our upper limit. And so in this case, we're looking at a CM and CMK of 1 at 3 sigma. But we would really like to get our values closer for our tool value. And so this would be a little bit more representative of what we saw with that particular value, where even if we had a shift of 1.5 sigma through the, we're still well within our lower and upper limits for that particular tool. And so then it gives us the ability to look at other things that may be an issue with the process. So we have the tool performing correctly. So then it gives us the ability to look at other things within the operation, whether that being the material that's being used. Was there a material change? Was there a vendor change that may be using a different vendor for the fasteners? You can look at different operators and how they're using the tool. But again, this gives you the ability to check the process, and you're eliminating the tool as the problem within the process. And so you then can focus on the external influences that may be being applied to the process. Again, differences in users, differences in how they set up to do their particular application. And so this can be really helpful in helping to improve your process control by doing the CM and CMK study for those particular tools that are in use. And so all of this, again, gives us the ability to capture data regarding how the tools are performing either before the assembly, during the assembly, and then we can check them again after the assembly with our auditing process or with the process control and R&D types of issues. So that's going to lead us to our questions and answers for today. So let's go ahead and see what questions we might have. So Chris, do we have any questions?
Hello, Dave. Yeah, we have some questions. One of the first ones was, is tightening torque, does that have to be equal to the loosening torque for applications?
Yeah, so that falls kind of what we talked about with the breakaway torque. It really depends on the fastener that's being used, but in most cases, it does not take more torque to loosen a fastener than it does during the application. As I mentioned, there can be some torsional forces within the fastener, because as it begins to stretch, you may get some torsional forces that are going to aid in that removal value. So it can be lower than what you may see it being applied.
All right, thanks. Next question we had was, is there like a recommended number of test data readings to use when doing a calibration?
So, excuse me. Calibration, typical, it's going to be for a certificate. You're looking at 5 readings, but it just depends on what your process might consider. You may want to do 10 readings. You may want to do some other variant of whatever readings you might like. But we do have customers that when they're doing their calibration, they're using the ISO standard and they're just taking that particular value number for those readings. But we do have other customers that have very critical type of applications. And what they'll do is they actually test their tool before it's being used. So they may test it 10 times to make sure it's still within its spec, go use the tool once, and then come back and test it again at a value of either 5 to 10 times. So it just depends on what level of concern you may have for your applications, but the typical one is going to be 5 readings.
All right, thanks. Another question we had was, is it better to measure torque post-tightening process?
Now it's actually better to, if you can measure it during the actual installation. That way you're getting all of the variables that go into the actual torque value, whether that is the frictional forces that are on the threads, the frictional forces that are on the bearing surfaces, and the RPM that's happening as it's being done. That's going to give you a much more accurate value than it would be if you're trying to validate that reading afterwards. But again, depending on the type of test that you want to use or the type of tool that you may want to use, you can give you that correlation between an install value and the auditing value. So it's ideal to be able to test on your application, on your part. And again, you can do that with a rotary type sensor and a torque analyzer.
All right, thanks, Dave. Another question we had is zeroing out each tool test data important?
I'm thinking the question might be zeroing out the analyzer.
Yeah.
Maybe, but yeah, you'd want to make sure that the analyzer is at its resting value of 0 before you do your testing for each rundown.
Another question we had was, what's the difference between the torque verification and torque validation process?
So this gives you the ability to actually test your tool in between calibration cycles. So you don't get the notification of a tool that's come back from calibration that was out of tolerance when it was found at the calibration testing. And so the validation and verification process allows you to make sure that the tool is still operating within its limits before it goes out for calibration during the time that it's being used. So you're monitoring that tool, giving it or understanding how that tool is performing in between calibration cycles. So you notice that if a tool is coming out of its specification, that tool can either be looked at, recalibrated, or adjusted.
All right, Dave. That's all the questions I had for today.
All right. Thank you very much for joining us today. We look forward to seeing you again next month with our next series on the theory of torque, where we're giving a basic Torque 101 type of webinar. So thanks very much and have a great day.